So, next 15 minutes I will do something slightly difficult task. There is a bottleneck in OpenMP because of cache issues. Okay. So, I will show you by this example A x equal to y. Okay. So, A is a matrix. So, x is a vector, right. So, x equal to y, you understand, no, linear equations. So, x is unknown, y is given, right. So, multiply a matrix with a vector. So, I did not run it on Colab, I ran it on MacBook Pro because I wanted to run for 4 processes. This was done before. Okay, so strategy is, what is strategy for A x equal to y? So, A is a matrix. The matrix size can be m comma n, which can be different. M is not equal to n, need not be equal to n, and x is here and y will come. We do not have many process. We have, when in a single process, a single laptop or desktop, we can have 4, 8, 32, 64 max, okay, in a workstation. So, I divide this data A like that in process. Okay. So, this is 4 process. So, this x will go and multiply by each row. You understand, no? I mean, everybody knows x equal to y. So, I have this row, I multiply this row with this x. So, I get a number and sum it up and I put it here. So, the division we need to worry about. I divide only A, don't divide x, okay, that will be a problem. So, divide A, but x is a one dimensional array, not so big deal, but Ax, so basically we divide A and this part can be done simultaneously. So, process 0 will compute these guys, process 1 will compute these guys, 2 will compute these and 3 will compute this. Clear? So, that is a strategy. So, this is a code, pretty simple, no big deal. So, you just focus on, well, I just said range is this, by given index I can compute the range, start and end. It is slightly different syntax, but the same idea. Okay. I am dividing the rows of A. Okay. So, these rows of A and multiply by vector. So, I get a product and this will be start to end. So, this vectors operation. Okay. So, if you look at it, I am going to do it simultaneously. In fact, this is all vectorized. This guy does that, this guy does, the next time it will do this, next time will not next time, in fact, it can be simultaneously if there is a vectorization possible. Okay. So, it is done, supposed to do vectorized way, start to end. So, it is set of rows and this is a set of columns, colon is set of columns, multiply by column, multiply by row of the vector and compute it. So, this is straightforward, no? I just go the simple one, the first one. Okay. So, I just create a process, argument, append it, start, and then I can just, but the data is already there. So, I am not doing any sum or something, okay, here. So, I do not need a manager really. My data, where is my product? Product is stored here, shared memory. This is my product, y, this is y. Okay. Now, it turns out, so this is the program is there in your Colab, and so, and this is called GC, garbage collector. Okay. So, garbage collector is when you delete some array, you can collect the, you can basically free it up. Now, the results are here. So, I performed this operation for 3 different configurations. So, array A is 8000 squared or 8 million times 8 or 8 by 8 million. So, array there are 3 possibilities, right, okay, and the number of operations are the same. for all 3 cases. Yes. So, my array A has been, there are 3 types of arrays. Array A is 8000 by 8000 or 8 million by 8 or 8 by 8 million. My array X of different sizes. Array X here is 8000, array here is 8, size 8 only, here it is, array X is big, but you can just convince yourself the number of multiplication are the same. Now, with process 1, for the 3 cases I get take basically these are the timings. This one is the fastest. Okay. Now, with process 2 there is some speed up, time should decrease, no, 2 process it decreased, and with process 4 it decreased further, and I can compute the ratios. So, 0.83 is the ratio of 0.319 divided by 0.528, that is efficiency, right. We discussed the thing T1 divided by T2 divided by 2, well this one is T1 divided by 2 T2, this is T1 divided by 4 T2 at 4 T4. If it is perfect scaling, then it should be 1. No, this one, I am sorry, this is this one. But 6.65 is not good, but okay, okay, not bad. There is some speed up here. If you look at it here, the worst efficiency is for this case, the last case, 8 by 8000. It is a 0.34, which is not good at all. So, when I go from 2 to 4, I do not get any speed up, negligible, okay, that is within error bars. The question is why there is such a low efficiency for 8 by 8 million, this case, okay. Curious, no, why does it happen? And this is a generic phenomenon, okay, and that is what we need to understand why. So, this is because of cache. In shared memory, the data is, well, not in CPU, data goes into cache, from RAM to cache, and CPU works on the cache data and produces output. So, let us first understand the cache thing. Okay. So, you have to pay attention to this part, this is the tricky part. So, main memory is here, and this is process P0, P1, okay, P1, P0. Each of them has their own cache, separate cache, L1 cache. I am not talking about L3 cache, L1 cache which is the closest. Each of them has a private L1 cache, and they will work with their private data, private cache. Now, the question you can immediately understand, if there is a memory location X, now is being copied here, is copied here, you must guarantee that these 3 X values are the same, otherwise there is a problem, right. I can't have roll number of your in one class, this class is one roll number, in another class another roll number, right. So, that is the problem. So, this is called cache coherence. So, this cache values must be equal, and that should be equal to the what is there in memory, okay, and that can be a problem in some operations. Okay. So, let us look at it this cache incoherence problem. So, you have to watch the movie carefully. This is from Wikipedia. So, this is first start with 5. So, it is asking 5 to come, read X, 5 coming in, 5 comes in here, okay. So far good. X plus 3, so it has become 8, this is X plus 5 with 10. So, this was called X plus 5 and this was X plus 3, okay. Now, this guy is 8 and that guy is 10. Now, what should I store in the memory? Should I store 8 or should I store 10? Now, it is a total chaos, right, because it is the same variable X. So, we have to do it in sequence and we have to make sure that it is all consistent. Your algorithm should not create this kind of problem. So, let us look at cache coherence issue. So, just this is happening one more, read X 5 5 both the cache have it now. The first cache is 8 now, x plus 3, second one is 13. By the way, 8 was written there, once this became 13. So, please recall, okay, I want to stop this, I think. So, let us see again, this became 5, then this became 5, this becomes 8, 8 is copied there, 8 is copied back, okay, that then x plus 5 it became 13, 13 is put there and copied back. So, this memory to cache you have to make sure if P1 is changing something into cache, then it goes to the RAM and the RAM sends it back to P2 cache. It is a hugely expensive operation. Remember, cache to memory was an expensive read write. So, it has to go from P1 cache to memory, then P2 cache to make consistency, and okay, that is what is the time cost. So, let us look at it. So, this is the definition. Incoherent caches, caches have different values of a single address location. We do not want this. Cache coherence is when values in all the caches, cache copies are same and the same is RAM. So, there is something called cache line. So, when you read data from memory to cache, it is not done one number by one number, it is done in a big chunk. So, we send 8 double values, each double value is 8 bytes. So, 64 bytes are written in one shot. Why is it written one shot? Well, read write is expensive. So, you do not, I mean, I want to, you go home, then you do not carry one item, well, you carry in a bag, whatever you need for your semester. So, we basically bring packet of data. So, that is what is being done there. So, it is brought in bigger chunks. By the way, GPU does not have all these issues. So, GPU is basically very streamlined military type of operation. So, it does not have this confusion stuff. So, we will discuss that later. So, this cache line basically gets this data in 8 double and is being copied. Okay. This because we need those data often next, like for addition, for arrays. I need big chunk of data to do vectorized operation. Okay, so, get a big chunk. Okay, so, now let us look at this case, which is the problem case. It is 8 by 8 million. So, I divide into 4 processors, right, they are different colors, P0. So, T0 is same as P0, okay, T1, T2, T3. So, there are 8 rows, right. So, 8 rows means each process is getting how many rows? 2 rows, 4 process, right. So, 2 rows. Now, X is a big long array, long 1D array, 8000. So, according to our strategy, what should I do? This guy will I multiply element by element, sum it up and put it here, multiply element by element, put it here, multiply element by element. So, these are 8 values are obtained by summing this big vector sums, doing some big vector sums, okay, and this should be fast, right. I mean, this is very nice. I have 8 million numbers to be added simultaneously, should be super fast, but this is a problem. What the problem is? My cache line is 8 double. So, this y is sitting in a cache, it is one area of the cache. So, if I look at the cache has a lot of data, but these guys will be basically one, all the numbers are sitting in one location, one area. Now, so look, the P0, the T0 process 0 is going to affect these, right, going to change it. Now, P1 is also doing it and changing these, but while changing it, memory has some old values, right, memory has old values, no? I mean, before changing the memory has old values, and these old values and new values, well, let us say P 0 will write these old values in RAM, new values in RAM, this RAM, writing it there, fine. But then the P 1 says, well, so here this cache line, this okay, what is going to happen is I need to update. So, this is not updated, this is to be updated, this is not updated here. And what does P 0 see? This P 0 sees I have updated mine. So, P 0 says I have updated mine, okay, and so these two are same, but then okay, so just give me 1 minute. So, this P 1 this is going to see that this is by the way. So, one thing, this cache, this whole area is common to, well, common means it is copied in for all the processors. This cache will be, cache has 8 numbers. It is not that T 1 cache has only 2 numbers, T 1 has all 8 numbers, these 8 numbers. All the processors, all procs have Y in cache. Okay. Now, this guy has updated. So, that means P 0 the cache, well, so I need to, we should make let us think of P 0 and P 1. These two are P 0 cache, P 1 cache, these are updated in the RAM, but P 1 has not updated it. P 1 did not compute it. So, P 1 has not updated it. So, what should happen really? When P 0 updates these values, it goes to the RAM, then RAM copies back into these, otherwise there will be complaint. Because P 0 has updated these two values of Y, but P 1 does not have that information, got it. So, RAM has to do much more work. So, P 0 writes to RAM, then RAM has to write to P 1, same thing happens for the next set. So, all these rewrite are to happen, and confusion, this is a confusion of cache coherence. And because these numbers, I expect them only, well, you should report only 2 numbers, each guy should compute only 2 numbers and worry about their own data. But it turns out they have all 8 of them, and this, well, your numbers are different. So, there is just lot of confusion. Okay, I mean, they are not wrong, but it is not updated instantly. Got this? This is a problem. So, this is because of false sharing. This is called false share. Yeah. Unfortunately, the full 8 numbers are there in each of cache of each of the processors, and they can see their memory. So, what P 1 sees? P 1 sees the RAM in the RAM location. So, 0th one, yes, and if it does not, then it says, well, there is a problem, you have done something wrong. RAM is updated, but mine, I do not have the fresh numbers. So, I update it. So, well, finally algorithm will update it, but this is expensive in terms of time. You got it? So, P 0 updates it, it goes to the RAM, but P 1 has not updated those 2 values, because P 1 does not update, P 1 is not job of P 1 to update them. So, RAM has to update them, and that will take time. So, there is another issue, that there may be small locations. So, 8 million by 8 million is not going to be done in one shot. So, there may be basically temporary sums. So, that could be another issue, but we are ignoring that part. But we are assuming that, okay, we get a number which is put in the cache, and they are not coherent, because the cache line is 8 bytes, 8 double, that is the problem. So, false sharing occurs when 2 processors share a cache line. So, they are sharing a cache line, and a T 0 modifies Y 0 in cache, that is what I have written, but not in RAM. T 1 tries to modify Y 2 in cache, however, it raises objection when it finds Y 0 is not updated. Okay. So, the solution is of course update as soon as you are done. And then another thing is called private memory. So, you can define private. So, for each processor these two numbers are private, okay. But I am not doing it today, maybe we do it later, but the private is what is thing. So, the processor has to update memory variables many times and this is expensive. Fortunately, this thing does not happen for other cases, other two cases, 8 million by 8 million or 8000 by 8000. Okay. There is some places it may occur, it will occur, but not overall, not for maximum. So, this is 8. So, 8 million by 8, this is 8 million by 8. So, my what is the size of Y array is big, is 8 million, this is 8 million. Now, cached lines will be 888 bytes, right, this is cached line. So, this cached line and this cached lines are different. Cached line for P0 and cached line for P1 are mostly different, right, except there may be some overlap here, cached line may have overlap here. So, there is a possibility of cache issue here if this cache boundary is not well defined, but we expect to be improbable. Okay. And moreover, there is another issue that when T1 is doing it here, so this would have been already done before. Okay. This is updated and this will be updated in RAM itself, but this part when is updating it, this will find that okay, well, green updates RAM and RAM has updated inside the cache of P0. So, there may not be an issue, but there is a potential problem at the boundaries, but overall this is safe from cache line issues, and similar things happens for the other case too. It is this is 8000 and not so common. Okay, summary, false arrays affect 8 by 8 million case maximally. We need to be careful about this. So, OpenMP performance are hit, this is one of the reasons, and but MPI does not suffer from this. MPI data is not shared. So, these Y's are their own different stuff, they do not worry about 8 numbers, it worries about 2 numbers by design. Data is not shared in MPI. So, MPI can be faster because of this reason. Okay, there are other issues of multiprocessing function which I did not do in today's lecture, terminate, queue, pipe, log, barrier. We will see whether we have time later and we may get into it. Okay, so, I would expect, I want you to compare the timings for shared memory and pool, and this is later MPI 4 pi.